Hello, everyone. Can you hear me? Can you hear my voice?
Yes.
Okay, good. And firstly, warmly welcome you to join the Ruijie Global Enterprise Quarter 3 Public Training. Okay, and as you can see on screen, the topic for this time is the simplified optical Ethernet solution, which is version. This is called CWDM. And in this course, we are going to introduce this solution, include the development background of this solution, the products in this solution, the deployment of the solution, and some common faults we could face if we use this solution. Okay. Okay, now before we start this part, I want to ask, since it's solution 3.0 is version 3, and before version 3 we have SOE 2 or 2.1, I want to ask that if any of you have ever used that solution. Yes or no? Have you ever used the SOE 2.1 or SOE 2.x? No? Okay, it doesn't matter. It doesn't matter. Actually, later we're going to introduce the difference between them, the difference between SOE 3.0 and the SOE 2.1. Okay, it doesn't matter. Don't worry about this. So since you didn't use it before, now we are going to start the content and let's see what's the difference and let's see the main content of this solution. Okay, firstly, let's see the overview or the preface. It says that as Ruijie's top-tier offering, the SOE 3.0 outlines an enhanced architecture and incorporates cutting-edge hardware products to improve overall network reliability and minimize deployment costs. So from here, you can know this solution is mainly used to improve the reliability, and at the same time, we can minimize the cost of the whole network. This solution represents a significant advancement from previous SOE solutions, and therefore supports improved hardware deployment modes, aligned software functions. So this will also be the content we are going to introduce. For this reason, it will be beneficial to familiarize yourself with the overall concept of SOE and RGINC software functions before undertaking this course. But actually, as I just asked, most of you didn't use this before, didn't use SOE and RGINC, these kind of tools, these kind of solutions before. So it will be maybe a little difficult for you to understand the working principle of SOE 3.0, but actually don't worry about this. And of course, during the whole content, I'm going to introduce the detailed information to you. Okay, don't worry about this. And we hope that after finishing this part, you will be able to know the background, the benefits of SOE 3.0. And by the way, SOE stands for Simplified Optical Ethernet Solution. So from the name, I think you could get that. It's a kind of solution that the most obvious is that we use the optical fiber to replace the Ethernet cables, for example, twice paired, right? These kind of cables. And there are some other differences with the traditional network. Let's see it later. And we hope that you can understand the architecture of SOE 3.0, learn about new products, new software functions of SOE 3.0, and understand the deployment common faults of it. This is also the content of this course. Okay, let's get to the main content. First is the background and benefits. here at this page, you can see at least two solutions. On the left is SOE 3.0, or it's called CWDM. Let's see the working principle of this. As you can see here in this figure, sorry. Okay, as you can see here, on both sides is mux and demux are both two kinds of products. Okay, and no matter mux or demux are used to operate the signals. Okay, the signals in the fibers. Mux, demux, for example, we can aggregate multiple. You can see here we can aggregate multiple fibers into one, or demux means we can split, right? Split one signal into multiple, for example, multiple subsignals. And how to distinguish them, how to maybe aggregate or how to split them is based on their wavelengths. Because we all know that for this kind of signals, the main or the one of the important parameter is the wavelength. You can see here we have 1271, right? 1271 and 1311, 1351. Here, what we can see is the wavelength, and by checking the wavelength or by comparing the wavelengths, we can separate them. We can distinguish them. So in this case, on the cable between two sides, for example, on this cable, it can be used to transmit multiple signals with different wavelengths. And then after receiving this, for example, the signal is from left to right. So after receiving it, the Dmax will check, okay, after receiving the signal, how many types of wavelengths I have received. And based on the wavelengths, I can, for example, split them into different types. For example, number 1, number 3, number 5 are the signals received from the left side. And I split them and send them to the maybe the downstream devices, right? Okay, this is the, what can I say? This is the main working principle of CWDM. Just like this figure, you can see, let's check. By building different types of bridges, we can distinguish the cars on the road. For example, the cars and the two different directions can be isolated, right? Physically isolated. And even the cars with different speed can be separated. Okay, so in this way, we can improve the efficiency of the whole road and can improve the reliability. Of course, if we mixed all the cars together, it would be, how can I say, it would be more dangerous and more complex. Okay, this is the main idea of the CWDM solution or SOE 3.0 solution. Well, compared with that, let's see the architecture of SOE 2.1. Okay, you can see here, this is a very typical network architecture of the SOE 2.1. In this architecture, you can see the whole network can be separated into different layers. The indoor switch, or in another word, we can call that this is the access layer. And then from the name indoor switch, this switch is deployed inside the room, and it can be used to connect with the, for example, the indoor APs, the PCs, the cameras, this kind of clients or this kind of terminals. This is access layer. And then all the indoor switches is connected with the, for example, the OR optical switch. From the name OR optical switch, we can find out. From the OR optical switch, we can find that actually the cables we use the cables we use here actually are fibers, or in another word, are optical fibers, right? And then compared with the traditional Ethernet cables, the optical fibers have some advantages. Do you know what are the advantages of the optical fibers? You can think about it and maybe give me some feedback in the chat box. Okay, anyone knows that? Distance and bandwidth. Yes, very good. The advantages of the optical fibers. First is the distance, because as we all know that the Ethernet cables has a limitation, right? Or the copper we use normally has a limitation. The distance must be shorter than 100 meters, right? And next is the bandwidth. Normally, the image is not clear. Well, which image you mean? Okay, how about now?
Oh, that's fine.
It's fine?
Yeah, it's fine now.
Okay.
Yeah,
good,
yeah.
good.
Okay, clear. Good.
Okay, sorry for that. So let's go on. Okay, and just I asked a question that what's the advantage of the optical fibers, right? As you have answered, first is the distance, right? We can beyond 100 meters, and next is the bandwidth, right? Nowadays we have 10 gigabit or even higher 40, right? 40 gigabit ports and cables, okay? And so here in the SOE 2.1 solution, we replace the, for example, the coppers with optical fibers. So in this way, we can maybe make the distance between devices longer. In this way, we can maybe deploy the core switch very far away from for example, from the dormitories, from the libraries, right? We can make the network more simplified, right? More simplified, because without the limitation of distance, we can use fewer devices, right? We can use fewer devices in the network. Okay, and next, let's see. Except the OR optical switch on the right is the ODF. Let's say this. ODF can be used to connect with the indoor switches and the core switches. You can see from the figure, we can know that ODF is a kind of passive device. Do you know what's a passive device? Passive device means it's in another word, it's a device that can receive signals, forward signals, without the requirement of powers. Okay, without the requirement of power supply. And how does it work? You can think without power supply. So how does it work? It's physical, or it's based on the physical. For example, the wavelengths. For example, the rates. Right, based on this kind of physical parameters, they can distinguish different signals, can maybe aggregate them, can split them, can forward them. Okay. So this is also a very important advantage of SOE 2.1. Since it's a passive device, so it do not need power supply, and it's not running any operating systems. For example, for the or optical switches, maybe it's running RGOS. For example, for our PCs, it's running, for example, Windows, it's running Mac OS. So they need maintenance, but for ODF, it's a passive device. Maintenance is not required. If we use a lot of ODFs in the network to replace switches, it can reduce the workload of maintenance for our engineers, right? Okay, and next, let's see the figure here. This is a very typical connection method of the SOE 2.1. You can see here we have some ODF, right? We have core ODF, building ODF, and then at the access layer, we have some access switches. The access switches here could be the, for example, we have some models actually. We have some models SF 29 series, SF29 series switches, for example, SF2920 or SF2920U. Okay. The difference is that SF2920 is using RGOS, right? This is not. And our SF2920 is similar to the traditional switches, which are many used or many managed or configured by commands, while SF2920U is mainly managed by web page. Okay, you just need to know this. It's two types of products in SOE 2.1. And then this is the transparent distribution. It's transparent, so it will not operate the devices. And by connecting with ODF, the signals can get to the, you can see here, Dmax. After receiving it, Dmax, you can see the cable is connected at this part. Let's make it larger. Okay, the cable is connected with here, with this port, while the outbound, you can see the outbound interface is this one, it's here. So it means that this cable can be used to carry the multiple aggregated signals, and we will split them and connect with specific core switches with this port. Actually, this is the CWDM port. Okay. After knowing the architecture and the difference between SOE 2.1 and SOE 3.0, next, let's see. Let's actually make a summary, the advantages of SOE 3.0. First is the high requirements of our OM can be satisfied by SOE 3.0. The number of fiber cores on the core side is twice the number of access devices. Then the line cards of core devices have a dense distribution of cores, which poses challenges when operations need to be performed on specific ports, because it's very difficult for us to distinguish them. From this picture, you can easily find out that firstly, the number of cables, the number of ports are very large, and then actually it makes it looks very complex, right? Except that the optical transceivers on the core side need to be paired with those on the access side in a one-to-one manner. Because it must be matched, fixed matched. It's a one-to-one manner, resulting in complex deployments. Okay, and the next is no support for some scenarios, high deployment costs. This is also how can we see? This is also a shortage of SOE 2.1, and in another word, it's an advantage of the solution we're introducing now, 3.0. The deployment of a VSU on the core side will drive up cost, because since it's VSU, so at least we need two devices, and we need some extra configurations, extra devices to make it more reliable, right? Because the main function of VSU is to improve the reliability of the network, which is not desired by customers, because customers want to spend less money and get a better or get the best experience. A combiner and a transparent distribution device provide only 24 or 48 ports respectively. So the number of ports is limited in SOE 2.1. While in SOE 3.1, we have raised the number of ports. Later we're going to introduce it. and the number of ports limiting the application scenarios. Okay. After knowing these pain points, in other words, you can see this is a pain point, and at the same time, we can think this is the background of the SOE 3.0. Okay. Then let's see. After knowing the background, let's see the products of SOE 3.0. First is the chassis type line card. Okay, this is the line card, and that can be used or that can be added to some switches, right, to extend the function of the switch. Okay, and some small fixed port switches. So compared with the chassis type line cards, this is smaller and are suitable. Okay, are suitable for some small networks. Don't need that high-end devices. Okay, and the next is the transceiver, CWDM transceiver. You can see this CWDM transceiver only have one. Okay, only have one logical interface, but sorry, only have one physical interface, but actually it have 8 logical interface because we have separated the signals into 8 types with 8 different wavelengths. Okay, so one physical interface is matched with 8 logical interfaces. Okay, and the next is the transparent distribution device. Okay, this is also a transparent distribution device, but it's a latest version, which is version 2. It has some advantages compared with the transparent distribution device we just introduced in SOE 2.1. Okay, later when we introduce this device, you can find it. Okay, you can find. And next is a splitter. Splitter is from the name. Actually, the name is quite easy to understand. Split is used to split the signals. Okay, it has it has three interfaces. This is one interface, and here are 2 interfaces. So it has 3 interfaces. It can be used to split the signal. For example, one signal will be split into 2 same signals. Pay attention here. Or in another word, is hopping. Okay, 1 to 2 same signals. Okay. And this is a function of the splitter. And next is a transparent distribution device chase. This chase is a kind of device, or in other words, even it's not a device. Okay, it's not a network device. It's just a chase which can be used to fix these kind of devices, to fix the splitters, to fix the transparent distribution devices. Because if we want to fix these splitters, these transparent distribution devices in our cabinets, we must, for example, we must have a standard size. But obviously, from the figure you can find they are not matching the fixed or standard size. So we use, for example, you can see here, we can put the splitter. Let's make it larger. You can see this chase, and it has been tiered into 6 parts, actually. Part 1, part 2, 3, 4, 5, 6. It means that this chase can be used to fix 6 devices. For example, here we have for example, we put the distribution device here at the first part, and then this is another distribution device, and here we put the splitter, for example, S1, splitter 1, splitter 2, splitter 3, splitter 4. Right? It's just the example. How to fix these devices is based on the real network. Okay, the requirement in your network. But you just need to know the function of the chase is used to fix this kind of devices that not match the standard size. And next, you can see this chase on the 2 sides of this chase. is used to fix this change in the cabinet. Okay. Here are some devices. And next, let's see the architectures, deployment scenarios of these products. Let's go to the next page. This is the architecture for the single core scenario. Pay attention here. This is a single core. So you can only find one core switch in the network because this is a core side. This is a core side, and at the core side, there's only one core switch or CWDM switch. Here is an OR. Do you know what's the meaning of OR here? This is the, at the former page, let's go back to the former page, you can see. We have small fixed core switch or chase type line card, which can be added to some modular switches. Okay, so from here you can know OR means it could be a large switch which have installed the CWDM line cards, or it could be a small, it could be a small CWDM switch. It depends on the requirement of the network. And the small so many users. Okay, this is a single core scenario. And then let's see how to connect the cables here. Now at the access side, you can see this is the indoor switch, and the indoor switch will use a CWDM transceiver. If you can see it, I don't know if it's clear enough, but you can see, I think it's more clear now. There's a number on this transceiver. It's one. It's one. And actually, in this figure, it's a Chinese. It means access one. Access one, first, the access means this transceiver is used at the access side. And one means it's number one. As we see that, in this solution, we can distinguish the signals into 8 types. 1, 2, 3, 4, 5, 6, 7, 8. So this is the, and each type, for example, type 1 is, how can I say, is representing fixed wavelength. So on the other side, let's go back to the core side, you must choose. When you choose the CWDM optical transceiver, you must find the transceiver which number is 1. Okay, it's very, very important. And between them are the splitters, are the ODFs, ODF-A, ODF-B. Okay, it's not that complex. Okay, this is the single core scenarios. And except the single core scenarios, we have some other solutions. Let's see. Here are actually you can see three different scenarios. If the network is small, how can we define the network is small or large? You can see if the number of rooms is less than 700 rooms or below, we choose the single core architecture. We only have one core switch. Okay. While if it's more than 700 but less than 1500, so what we use is the multi-core, we call it multi-core architecture. We have 2 core switches, right? We have 2 core switches. And in this case, if we have 2 core switches, what we can use is, for example, we can deploy a VSU. We can use VSU on these core switches. So in this way, we can improve the reliability of the whole network. And since we have VSU, so you can see here, this kind of distribution switches are, we call it door up upstream links. It's, for example, on this switch on the left is connected with the left core switch and the right core switch. For the other one, it's the same. Okay, this is suitable for some large networks, which number of rooms is less than 1500. Or if we have even more rooms, you can see we can add the number of the switches. Here we have 2 CWDM switches. Here we can add them to 4 or even 6 and even more to satisfy the requirement of the network. Okay, so when you use this solution, you should think about the requirement of the network and design a suitable network architecture for the customers, for the users. Okay, and after knowing the architecture, next let's see the products. We have mentioned some products just now, right? For example, the splitter, for example, the latest version of the transparent distribution device, right? Okay, and next let's see the products and the convenience. The first product is the optical transceiver. Okay, and from these two figures, we cannot find out the difference. But from the name, I think you can find out. First is SFG LRSM, and the other is SFX LRSM. So the difference is here. This is G, this is X. Here you can see that normally when we see, for example, when we see the interface on the switches, we use G to represent gigabits, right, or 1 gigabit, while X is 10 actually, X is 10. So X means 10 gigabits, the bandwidth of the port. So here is the same. Let's see the integration of a combiner with a CWDM transceiver. Each CWDM transceiver supports single core optical fiber externally and 8 logical ports internally. This is the reason why we see that this kind of transceivers only have one physical port, but it have 8 logical ports. Okay, and the difference between them is that the first SFG is a 1 gigabit CWDM transceiver, and SFX is the 10 gigabit CWDM transceiver. Both SFG LRSM and SFX LRSM support single mode optical fibers. A transmission distance of 10 kilometers is a quite long distance, right? And the LC ports. Okay, this is the transceivers. We have 2 types of transceivers. You can select based on your requirements. And next is M18E, and this is 8SFX. This is 8SFG. So you can find here the difference. The main difference is also X and G. Right? As we just introduced, X means 10 gigabits, while G means 1 gigabit. Okay. After knowing the difference, let's see what's the function of this. What's this? First thing we should know what's this. This is the line cards. Line cards that can be added to the chassis switches. For some large switches, have the extended chase box, so we can install them into this chase, right? And then this switch can support CWDM. Okay, and from the name M18,000. From here we can know this is a extended line card developed for the switch, which is a very famous switch of region N18,000E. This is a switch. So for this kind of switches, we can use the line cards here to extend. Okay, so pay attention for this. When you see the line card which start with M and the number represents the version or the name of the switch models that can use these line cards. Okay. Each of the line cards provide 8 slots for inserting optical transceivers. Pay attention here. Here are the, you can see, here are the slots can be used to insert the transceivers. We can insert the transceivers in each part. In this way, one line card can provide 8 physical ports. So because we say that one transceiver can have one physical port, so we have 8 slots for these transceivers. So we have 8, right? We have 8 physical ports, and each transceiver is represents 8 logical ports. So in all, here each line card have 16 logical ports in total. In this way, we have improved the number of ports we support than the SOE 2.1, because we said that if the solution is SOE 2.1, it only supports 24, right? It supports, let's write this, it supports 48 or 24 ports. But for this line card, it supports, sorry, where? Okay, it supports 40, 60, 64 or 64 ports. The number of ports has been increased. And the main difference from existing line cards in the optical transceiver specifications, similar to the difference between 10 and the 40 gigabit cards and 100 gigabit cards. So the only difference is a rate. One is 1 gigabit, another is 10 gigabit. Okay, and the next is actually similar. From the name, we know that this is the line card for the switch 78 series switches. You can see developed based on the 78CX switches. Each of the line cards provide 8 slots. So 8 slots means 8 transceivers. 8 transceivers means 64 logical interfaces. Okay, and the difference between these two line cards is also the rate. This is SFX. This is SFG. So difference is 10 gigabit and 1 gigabit. Okay, and next is the we call it the small. See the okay. And let's see the difference between them. Each of the switches have a size of 1U. 1U means a U is the concept of the height. Is the height of the switch. Is 1U. Okay, 1U means in the cabinet it occupies 1 unit. The height is 1 unit. Okay, and provides 10. It have 10 optical transceiver ports. And the ports could be 1 gigabit or 10 gigabit, except that it offers 100 gigabit optical transceiver ports and 1 expansion card slot. Is it at this part? At this part, these 2 parts are the expansion card slots. Here we have already installed the cards, but if we, for example, if we release these 2 locks, and we can pour out this line card and replace with another one. Okay, replace with another one. And which line card you use here is based on your requirements in your real network. Okay, and next is S7620 series CWDM switch. Okay, and different from the switches we just introduced, the size is 2U, is higher. The size is 2U, is much higher. Much higher reference is support more transceiver ports. Okay. the number is 20 here. The number is 20, and except that 200 gigabit optical transceiver port and 1 expansion card salute, which is here, is similar. Okay, and next from the name we know that this is the expansion card for the 76 series switches. Okay, no matter 7610, 7620. Okay, both these two types are applicable to RGS 7610, RGS 7620 series switches. And let's see the difference between them. Obviously, from the figures, we can easily find out the difference between them. M7000 and 7600 provide 4 electrical ports and 4 25 gigahertz optical ports, while 2CQ provides 2 100 gigabit optical ports. So you can see here are 2 100 gigabits. Okay, this is 100 gigabit ports, while here are different, right? 4 electrical ports, here are electrical ports, and here are 4 25 gigabits optical ports. Okay, this is about the expansion cards. After introducing the switches, the expansion line cards, next let's see the RG Max and the RG Max box. Okay, you can see here RG Max 8 LC. LC is the means it have a pair of LC ports, right? Here are the LC ports. Here are LC ports. Okay, what the difference is here? Edge. The device on the right side and with edge. So what's the meaning of edge? Let's see this. These two devices are transparent distribution devices. Each of them can provide a maximum of 8 access ports, including 1 combiner port. Okay, this is a combiner port. COM means combiner. And edge features low insertion loss. This is the difference. This is the only difference between them. Edge features low insertion loss. Okay, and next is the RG Max box. We said that this is not a network device. It's just used to fix the Max devices, to fix the splitters we're going to introduce. Okay, and let's see, how does it work? Okay, how does it work? You can see here, this is the chase. This is the chase. And this, we say that it has 6 parts, but here, now it's empty. No devices inside, but we can insert, you can see here, we have insert some, this splitter, 3 splitters, and 3 Max, RG Max. Okay, and in this way, we can fix these devices to the cabinet. Okay, by using these 2 parts to fix them. It provides 6 device loops. Transparent distributing devices, splitters can be inserted into it. Okay, this is about the function of these 3 types of device. And next is the RG Max exit, or it's, in other words, it's commonly called splitter. For the name, splitter means it can be used to split the signals. Let's see. RG Max EXT, or the splitter, is a passive 1 to 2 splitter. 1 to 2 means from 1 and split it into 2, used as an expansion model for the transparent distribution device in a building. Supports 2 and door uplinks and the VSU scenarios. Pay attention here, VSU. Because we see that SOE 3.0 is more suitable for the VSU scenario. Why? Why is more suitable? One of the reasons is this device is a splitter. Because if we have two core switches, for example, we have two core switches, and the distribution switches should connect and send the same signals to these two core switches. So how can we send? This is the, how can I say? This is the optical network. If it's the this is the traditional network, we have some switches, so we can copy and send the same signals to two core switches. But here with the splitter, it's more convenient. Let's see. This splitter splits a signal. You can see a single optical signal from the COM port into two identical optical signals. It means that the COM port, for example, COM port here is this is a cable, is connected with a switch. So the switch will send a signal to the COM port. While now I want to send two same signals to the maybe upstream devices. So this signal will be split into two types, and we'll use two cables to connect with here, connect with core switch, connect with core switch. So in this case, the core switch can receive two same signals from the splitter, from the downstream devices. These signals are then transmitted through port 1, port 2, each with half of the power of the COM ports. So since, do you know the reason why the power is half? Why the power is half? Because if we use the traditional switches, the power will not be affected, or it's not power actually. The signals or the packet, the traffic will not be affected at all. But why here the power will be a half? You can think about this. You mean bandwidth rate? No, not the bandwidth rate. It's a power. Okay, let's see it. Because what we transmit here, firstly, what we transmit here is the optical, right? This is an optical device. So it's not the electrical signals inside. It's optical signals inside. And yes, very, very correct. Course is passive. It's passive. Because it's passive without any power supply. So the device, for example, the splitter, cannot supply power to the signals inside. So in this case, if we split the signal into two sides or two signals, of course the power will be a half. Okay. In another word, for example, now we have a bottle of water. If we have two maybe small bottles, so we put them in 1.5, right? But now if we have a water supply, right? We have, for example, we are nearing river, so we can directly get the power, get the water from the river, and we can make each small bottle fill, right? So this is the reason, because it's passive without any power supply. Furthermore, optical signals from port 1 or 2 can also be transmitted through the COM ports on another direction. Right? All the three ports are physically fixed, cannot be switched. Okay. Okay, this is a working principle of the splitter. You just need to know that firstly it's passive, and then it used to split the signal into two signals with half power. Okay, and next let's introduce the CWDM. CWDM transceivers. The high power model provide higher transmit power, receiving sensitivity than models with names not ending with edge. So what's the difference is that you can see here are the transceivers which name end with edge, but here is no edge. Which difference is that the high power models provide higher transmit power and receiving sensitivity. Okay, this is the difference. And for these transceivers, let's see some difference between them. First is here. This is A1 to 8. This is A1 to 4. So in this group, if we use this transceiver, there would be eight transceivers from 1 to 8. 8 transceivers in one group. But here we only have 4. So in which case we choose this type? This first type, in which case we choose the second type. It depends, right? It depends on how many transceivers you need based on your requirements. For example, based on your service in your network, you need 7. You need 7 transceivers. So which type you choose? Of course, you choose the first type. But if you only need 3, so you choose the second type. And next is the XG. You can see XG means this is a 10 gigabit. The bandwidth is different. So you should choose based on the requirement of the bandwidth, not the number of transceivers you need. You should select based on the bandwidth. Okay, and next is the XG, SFP, LR, A1 to 8 and A1 to 4. The difference is that these two models are not ending with edge. So it's what we say. Ending with edge represents higher transmitting power and receiving sensitivity. Okay, this is about the introduction of the CWDM transceivers. And about what we have just introduced, here is a summary. No matter the optical transceivers or at the core side, the switches, right? Here are switches. Here are four types of switches, and here are some line cards. Okay, about the detailed information, you can just check this table, or even you need more detailed information, you can find some documents, for example, the datasheet of these models of these devices. You can find the detailed, very, very detailed information inside. Okay, here we will not introduce this very detailed information in this training. Okay, and next is about the building side, the mux devices and mux splitter. Okay, let's see. From the name, we can easily find out. Here are the mux device. This is the splitter. This is the mux box, which is used to fix these devices. Here are some transceivers with different rates, with different number of transceivers in each group, and with different transmission powers. Okay, when you choose which to use, you should take these parameters into consideration. Okay, after this summary, next, let's see the software functions. Because what we have just introduced are all the hardware devices and hardware parameters. Next, what we're going to introduce is the software functions. Let's see. First is the result of the port. Because we see that, for example, each line card have 8 slots for the transceivers, and each transceiver represents 8 logical ports. So totally we have 64 logical interfaces. And if you want to check you can check the status of each of them. You can see here this figure. Now in this example, they are down, right? They are down, and the type is fiber. All the type of all of them are fibers. And if it's running normally, you can see some of the ports are down, some of the ports are up. So you can check the running status, and you can maybe analyze the faults in the network, do some troubleshooting based on the output here. Okay. And if it's not since here we use the line card as an example, while if we use the SF series switches, even we could have more ports, because some of them have 8 slots, some of them even have 20 slots. So we could have even more logical interfaces. But the method to check the status is the same. Okay, and next is about the master-slave mode for aggregate ports. Firstly, you should think about it. In which case we will use the master and slave mode? Or in which case we use aggregate port? Think about this. Or you can think about it according to the figure here. It's very obvious, right? This is VSU, this is VSL. We all know that if you have ever learned VSU, you could know that VSL is the link between 2 VSU switches. Okay, so here actually we are running VSU. We are running VSU because VSU can improve the reliability, can make the network more stable. In VSU scenarios, adopting the CWDM solution, downlink ports, where are the downlink ports? Where are the downlink ports in this figure? You can find it by yourself. Actually, it's here, right? It's here. The transceivers are the downlink ports. Of course, we have downlink, or we have downstream, upstream. From the core to the access is a downstream. We call it downstream. From access to core is upstream, right? Okay, so the transceivers are the downlink ports. They need to be configured as an aggregate port, and the master-slave mode need to be configured for the aggregate ports. Means that this here we need to enable the aggregate ports, and one of them will be master, one of them will be slave. So in normal cases, master ports works properly because it's a master, while the slave ports only receive optical signals. If master port is down, services are automatically switched to the slave ports. So we have a backup, right? We have a backup. But for this kind of aggregate port, since it's mandatory, it's not running LACP. So we all know that when we introduced the link aggregation, we know that link aggregation have 2 modes, the manual mode and the LACP mode. In the LACP mode, the protocol LACP itself can elite the master and the slave ports, right? But in the mandatory ports, it's not. So here we should, in the aggregate port, we choose the command aggregate port member active standby enable. So we will enable the active and standby modes. In this case, the standby mode or the port in the standby mode will not receive the signals. So here comes another word. Why do we? Because if we have 2 downstream ports, 2 physical downstream ports, and we can receive packets or signals from both ports, we can improve the reliability, right? If there is a packet loss at the master port, we can receive the packet from the backup one. But here, why do we should block it? Why should we block the standby port? The reason is that the traffic is the same. It's not the traffic received from two ports are the same. It's not necessary for us to receive two same packets. It will affect the working efficiency of the network. Right? Okay. This is about the master-slave mode for aggregate ports. Pay attention to this command and don't forget it when you configure it. And next is about the port priority configuration for master and slave member ports in the aggregate port. This is optional because even you do not configure, they will elect the master and the slave. But if you configure it, you can control. Actually, you can control which port is master, which port is slave. Okay. You can configure priorities for member ports of an aggregate port in master-slave mode. A smaller value indicates a higher priority, so 0 is the highest priority. If no priority is configured for a port, it will use the default value. And the port with smaller ports serves as a master port. So here you can configure the priority of one physical port. Pay attention here. The priority is configured on the physical port. For example, gigabit is net 01. Okay. In other words, the physical port is the member ports of the aggregation port. Okay. This is about the priority. And next, let's see the deployment flow and precautions. Because we have introduced the hardware, the software, so next would be the deployment and the precautions. And the next part will be about the deployment flow and precautions. So after introduction, the background, the hardwares, the softwares, next we are going to introduce how to deploy it. Okay, let's see the deploy flow. Okay, you can see here, it's separated into different stages, multiple stages. First is perform cavity. Let's see, lay out optical fibers from target rooms, right, to provide it with network access to the ODF in the distribution side. Extra low voltage, the ERV room. Okay, because normally the aggregation switches is located in the ERV room, but in our solution, the ODF is located in the ERV room. Lay out optical fibers from the ODF in the distribution side ERV room to the core side ODF. So in this way, we can connect the switch side or the access side to the ODF and the ODF to the core side. Right? We have fitted the cable connection. And next is the unpack devices. So after connecting the cables, next we should unpack the devices. Means we should get the real devices we need, right? And next, check the number of devices. Number of devices based on their deployment positions. For example, here 8612 means from here maybe we can figure out if it's deployed at the 8th floor, and the room number is 612. Okay, so in this way, it can make it clear for us to move. For example, we move this device, this switch, to the specific room. And at the same time, you can see here, we have installed or we have inserted the transceivers. And you should pay attention. The number of the transceiver must be matched with the transceiver on the other side. Here is one, so on the other side, it must match this transceiver. Okay, it's very, very important. And next is install access switches. Deploy access switches in weak current boxes and light up the fiber pan to check connectivity of the optical fibers from the target rooms to the ODF in the ERV room. Pay attention, here is a very important tool. Let's see, it's called fiber pan. Fiber pan is a kind of light. Okay, it's a kind of light. It can, for example, if you connect the fiber pan with the fiber, it will set off the light, and on the other side, you will see, okay, if I can see the color, normally the color is red. So if I can see it's red, so it means I have received or I can receive the signal. It means the connection is very good, right? Okay, this is the first steps. And next, install transparent distribution devices in a row. Transparent distribution devices is the, as you can see here in this figure, right? We install it in the row, determine the number of required RG max devices based on the number of access devices deployed in the building. For example, in this building, we have about 100 rooms, we have 200 rooms, we have 10 rooms, we have 50 rooms. The number will affect the number of rooms is related to the number of RG max devices we need, right? Okay, and install transparent distribution devices to the rock. It's similar. And connect jumpers in the EOV rooms. You can see here. Connect jumpers is the connection between the the jumpers here represents the short fiber cables between the transparent distribution device and the other devices, the switches and others, and the ODF. Okay, it's called jumper. Record the mapping between optical fibers on the ODF and access switches with help of the lightning operations described above. Use jumpers to connect the transparent distribution devices to the distribution side ODF. Okay, so it's a short optical fiber connected with the ODF and the distribution device. And next, install core devices in the row. So after finishing the installation of the distribution layer, next is a core layer. We should install the core switches. You can see here are the core switches. And for these core switches, we are not, you can see the slots are empty, means we haven't inserted the CWDM transceivers anymore. So let's see, install core switches, line cards, optical transceivers, replace SDN controllers in a row. Pay attention here, it's very important. Here mentioned the concept called SDN controllers. Do you know what's the SDN controller mentioned here? What's it? Or do you know, maybe you can share any information you know about it with me. For example, the name of the model, the function of it, or any other information you know about the SDN controllers. Since there's a latency, so let's wait a moment for your feedback. Anything you know about this can share with us. Okay, maybe you didn't use it before. Maybe you didn't use it before, but it's very important. So here we will spend a few time on it. Okay, the SDN controller is commonly used in SOE solutions. You can see, you should think about the reason. Because, as we said that, if the number of rooms is less than 700, right, we think it's more network. If it's about 1,500, we think it's large. Even it could be more than 3,000 rooms. It's a quite large network. Even for common users, if we have 700 rooms to manage, it's already very, very large. Okay, I see. I find a feedback called INC, right? It's very good. The nowadays SDN controller, what we use in the SOE solution is INC. Okay, it's INC, or it's also called INC Pro. Okay, it's a kind of SDN controller, and the main function of SDN controller is that it supports a lot of functions. For example, it can manage the device, means operation and the maintenance. It can configure the device. It can, for example, it can deliver configurations to different types of switches, different types of devices. Okay, this is about configuration. And except that it can how can I say, it can automatically replace some devices. For example, some devices network is 40. Normally, we should replace it with a new device and configure the new device manually. But with INC floor, the controller can detect the replacing of the device and deliver the correct configurations to the new device automatically. Okay, and about INC floor, later we will have a slide to introduce it. Okay, and next, let's see, connect jumpers to the core devices. So here on the other side, the jumpers here are used to connect with the ODF and the core devices. Okay, this is about the steps. And next, perform device upgrade, basic commissioning. Upgrade the devices, plan service IP addresses and VLANs, perform the connectivity test on the access switches, and so on. Okay, and next is commission the INC, allocate management network segments, config device templates, find templates, and commission INC functions, replace devices, conduct optical link detection, conduct loop detection, and so on. Okay, so these 3 steps are related to INC, Some operations on INC should be done in these steps. And since here at last we're since at last we have finished the configuration, so INC can also be used to operate OM, right? Network of operation maintenance. Okay, this is about the project construction. Since we are going to have a detailed material to introduce the detailed information of INC, so later we will introduce it. We will not see any detailed information here. Okay, later we are going to introduce it. After knowing the deployment method or flows, next let's see the precautions. First, optical attenuation of link greatly affects the installation and deployment efficiency. In this case, we should ensure that in the 1 gigabit scenarios, RX optical power of the core side SFG model should be greater than, you can see here, should be greater than 14. And that of the access side 1 gigabit CWDM transceivers should be greater than 20, right? So here means we should pay attention to the power. And the second point, connect the single core optical fiber to the combiner port and the dual core optical fiber to the splitter port. Because if it's a dual core, so we should use VSU. If we use VSU, we must have the splitter to split the signal into 2 parts. And 3, if the optical signal strength is too large during on-site construction, add the optical attenuators. The attenuator looks like this. Okay, this is attenuator. It can be, normally we have fiber, right? And at the end of the fiber actually is a LC interface. And on the LC interface, if we think the strength is too large, so we should, you can see here, we should connect the optical attenuator to it, so it can affect the strength. Okay, affect the strength. Next, ensure that the numbers of access side CWDM transceivers map to the numbers of splitter ports on the transparent distribution devices in a 1-to-1 manner, as shown in the following figure. It is a 1-to-1 manner. It must match. Okay, must match. Okay, next is the common force. Common force means the common force we put phase, and of course, except the common force, we're going to give you some troubleshooting ideas. Let's see. The fourth symptom is that in a core side VSU scenario, a core side port cannot go up after an optical transceiver. Okay, sorry for that. Let's go. A core side port cannot go up. And after an optical transceiver is inserted into the port, the following use is interface 10.1066 and 3.066 as example. From the description here, we know that the problem is that we have inserted the transceiver, but the port is still down. What's the problem? Let's see. Here are the troubleshooting ideas. Check whether the interface is shut down. Because if the interface is shut down manually, it will be down, no matter the running status of the physical ports, physical cables. And second, check whether the port is added to an aggregate port. If it's added to an aggregate port, it will be affected. And three, if the port is added to an aggregate port, check whether the master slave mode is enabled for the aggregate port. Because if it's a slave port, right, it will be affected. The four, check whether CWDM transceivers are connected correctly. That is, check whether the CWDM transceiver channel of the access device matches that of the core side. So here comes the problem. At the core side and the access side, the transceivers must match. Match means the number should be the same. At the access side, if the number of the transceiver is 1, so on the core side, it must be the same 1. Okay, so how to check? Use the command here. Show int 10.1066 trans. So we can check. You can see the output here, and of course you should use a same command on the other side to check if they match. Okay, if it match, we still not find out the reason. So the next step 5, check whether the rate of the local port is consistent with that of the peer. Core side CWDM transceivers do not support rate auto negotiation, and their rates need to be adjusted manually. So if the rate do not match, it will also affect. The following lists the standard connections. Okay, here are two options. SFX part connect with SFX model, and then connect with 10 gigabit CWDM transceiver, 10 gigabit port on the access device as an optic port. If it's 1 gigabit, it's similar. Okay. And if we still cannot find out the reason, let's go check DDM. Check DDM information of the core device and the interface to determine whether the current and the voltage are abnormal. If yes, transceiver may be damaged. While if it's not, or if it's abnormal, right? Check DDM information of the core device and interface to determine when the optical signals are sent and received normally. Okay, if it's abnormal, we should replace the transceivers and have a try. We replace the device, have a try, and so on. Okay, this is the common faults we could face and the ideas of troubleshooting. Following these ideas, I think it's easy for you to find out the reason. And next fault, let's see. The master slave mode cannot be enabled on the aggregate ports. I think it's much easier for you. Let's see. Firstly, check that the aggregate port contains no more than 2 members. If it's more than 2 members, we cannot enable it. 2, check whether the correct ports are selected. If a configured port is a common port, master slave mode cannot be enabled. Okay, and you can also check. Also check the output here. AP member should be DMAX inner port, means the port type is wrong. You should change the port. 3, check whether the member ports use different channels. If yes, the mode cannot be enabled for aggregate ports. Okay. To check the channels is similar as the troubleshooting ideas we just introduced. Okay, after knowing the common faults and the troubleshooting ideas, next let's see a question. Okay, and by checking this question, we can find out if I have understand this course or not. First, let's see the question is that which of the following statements about SOE 3.0 is correct? Pay attention here. Which is correct? A, RG marks exit. What says? Please, firstly, I want to ask, what says? This is a splitter, right? This is a splitter. It's a splitter and it can implement one-to-one optical splitting. Therefore, it needs a power supply. You think it's correct or incorrect? A is false. Okay, A is false. Why? Why do you think A is false? Because it do not need a power supply. Right? It's a passive device. Okay, it's a passive device. Yeah, and at the same time, it's 1 to 2. 1 to 2 optical splitting. Split 1 into 2 signals. Very good. And the next B, SFG LRSM and SFX LRSM support grid auto negotiation. You think it's true or false? The main point is that does it support auto negotiation or not? As I remember when we introduced the troubleshooting, we said that it do not support. Auto negotiation is not supported. And C, both the master and the slave ports of the aggregate port can transmit and receive optical signals. If the master port is down, services are automatically switched to the slave port. You think choose 3 is correct or incorrect? Actually, it's very obvious, right? It's incorrect because it says that master and slave can transmit and receive signals. No, if both of them can transmit and receive signals, why do we need to elect master and slave, right? So it's false. D, in VSU scenarios, adopting this solution, 4 side ports need to be configured as an aggregate port, and the master slave mode need to be configured for the aggregate port. Is correct. Here, which is correct? We choose D. Okay, we choose D. Okay, and next, let's make a summary. At this part, we have introduced the background benefits of the solution, the architecture of the solution, and the new products we have introduced, softwares we have introduced, deployment process, and the common faults troubleshooting ideas are included. This is about the introduction of SOE 3.0. Okay, and after finishing this part, after introducing the solution, when we see the summary, I think you will get a little, what can I say, get a little confused. Because when we introduced the deployment process, we said that at last, after connecting the cables, after installing the devices, installing the transceivers, and if we want to configure the device, what we should use is INC. So what's INC? What's the function of INC and how to use INC? I think some of you are not clear, right? Or you are very interested in this product. It's called INC. So next, let's see what is it and how to use it.